Laniakea supercluster, galaxies appear to move toward an unexplained mass known as the Great Attractor. If similar anomalies exist on even larger cosmic scales, fast-traveling galaxies could be responding to these unseen forces. Conversely, instead of being drawn toward a mass concentration, they might be repelled by voids, massive underdense regions that create gravitational imbalances. Tracking their trajectories over millions of years could help astronomers identify these hidden structures. Another possibility is that some of these galaxies could be escaping the universe itself. If space is expanding at an accelerating rate, certain objects may reach the cosmic event horizon, a boundary beyond which they recede faster than the speed of light due to spacetime expansion. From our perspective, they would fade into infrared darkness, never to be seen again. If one of these high-velocity galaxies breaks free from the cosmic web, the large-scale structure of interconnected galaxy filaments, completely space where interactions are minimal. Some physicists speculate that if spacetime has hidden topologies, wormholes, or interdimensional pathways, such a galaxy could theoretically exit into another universe, making it unobservable forever. If astronomers detect a stellar system that appears to be vanishing without explanation, it could provide the first direct evidence of such an event. While most of these galaxies are thought to move away from major structures, some might eventually collide with others at extreme velocities. A high-speed impact between two galaxies traveling at thousands of kilometers per second would release unimaginable amounts of energy, possibly creating an entirely new class of high-energy astrophysical events. Such a hypercollision could trigger the most violent starbursts ever observed, compressing gas into dense clouds that rapidly form new stars. However, it could also lead to the destruction of galactic structures, tearing apart stellar systems and forming long tidal streams of stars and gas stretching across millions of light-years. If one of these fast-moving galaxies collides with a normal galaxy, it might even lead to the formation of an ultramassive black hole, disrupting the gravitational balance of its surroundings. Detecting such an event would provide valuable insights into the limits of cosmic energy transfer and the behavior of galaxies under extreme conditions. Another strange idea is that some of these galaxies might not be what they seem. Certain anomalies in their motion could indicate that they are faint relics from the early universe. If a galaxy formed soon after the Big Bang and was ejected at high speed, its light might only now be reaching us, making it appear as though it exists in a different cosmic epoch. Others proposed that some of these high-velocity galaxies could be composed mostly of dark matter, making them nearly invisible except for their gravitational effects. If such formations exist, they could be drifting through space largely undetected, interacting only through gravity. Even more speculative is the idea that some of these fast-traveling galaxies might be holographic projections or manifestations of unknown physics, possibly revealing hidden dimensions or an emergent cosmic order. Future deep space surveys could help determine whether they are entirely normal objects or something far stranger. If an intelligent civilization evolved inside one of these high-velocity galaxies, its experience of the universe would be radically different from our own. Due to relativistic time dilation, time for the inhabitants of such a galaxy would slow down compared to the rest of the cosmos. If their stellar system were moving at a significant fraction of the speed of light, billions of years could pass for the outside universe while only a few thousand years pass for them. The motion of their galaxy through intergalactic space would also expose them to extreme cosmic radiation, which could require either advanced shielding technologies or biological adaptations to survive. If such a civilization were aware of their home galaxy's extreme velocity, they might attempt to influence its motion, either to slow it down or to direct it toward a particular region of the universe. If astronomers ever detect anomalous energy signatures or signals from a fast-moving galaxy, it could be evidence of an advanced civilization adapting to an extreme cosmic environment. Future telescopes such as the James Webb Space Telescope, the Vera Rubin Observatory, and new gravitational wave detectors will allow scientists to study ultra-fast galaxies in greater detail. Among the most anticipated discoveries is the detection of the first relativistic stellar system, one moving at over 50% of the speed of light, which would challenge our understanding of gravity and dark matter. Another breakthrough could be finding a high-velocity galaxy that unexpectedly changes trajectory, suggesting the influence of unknown forces or even artificial manipulation. If one of these cosmic travelers is observed to vanish completely, it might provide the first observational evidence of cosmic gateways, wormholes, or higher-dimensional structures. Additionally, detecting a galactic hypercollision would reveal how energy transfers at the largest scales. The study of these extreme objects remains one of the most exciting frontiers in astrophysics. Whether they result from gravitational interactions, unknown cosmic forces, or even signs of intelligent engineering, such fast-moving galaxies push the boundaries of what we consider possible. As observational capabilities improve, we may soon uncover their true nature, possibly redefining our understanding of space, time, and the fate of the universe. If these high-speed galaxies exist in significant numbers, they may not be isolated anomalies but rather part of a greater cosmic pattern that has yet to be fully understood. Their existence challenges current astrophysical models, pushing the limits of our knowledge about gravity, cosmic expansion, and galactic evolution. They could also be linked to the formation of large-scale structures, revealing an unknown mechanism governing their motion at extreme velocities. One intriguing possibility is that these galaxies are not randomly propelled but instead follow gravitational highways formed by dark matter filaments. Some cosmologists propose that dark matter is distributed in a way that creates massive intergalactic superhighways, allowing certain stellar systems to move faster than expected. If this is true, these cosmic wanderers could provide crucial evidence about the large-scale structure and distribution of dark matter in the universe. Another theory suggests that fast-moving galaxies might be influenced by cosmic voids, vast empty regions with little to no matter. Instead of being pulled toward massive objects, these stellar formations could be repelled by these underdense regions, accelerating outward. Some scientists speculate that dark energy, the mysterious force driving the universe's expansion, might have local variations that push galaxies away rather than simply expanding space uniformly. If such galaxies are disproportionately found near cosmic voids, this could suggest that dark energy is more complex than previously thought. There is also the possibility that unknown fundamental forces accelerate these galaxies. While standard physics describes gravity as the dominant force at cosmic scales, alternative theories propose additional interactions affecting galaxies and clusters. If ultrafast galaxies accelerate in ways that cannot be explained by known gravitational effects, this could indicate the presence of a new fundamental force shaping the universe. Some researchers speculate that these stellar systems might be relics from an earlier phase of cosmic evolution. If physical laws or interactions between matter and dark matter differed in the early universe, certain galaxies may have been propelled to extreme velocities billions of years ago. This could mean that rather than being anomalies, these objects are remnants of a primordial event, offering insight into physics that no longer operates today. Another question is whether some of these galaxies might be artificial. If an advanced civilization had technology capable of manipulating gravitational fields, it could potentially control the motion of an entire galaxy. This could be done to escape a dangerous region of space, navigate toward a desired location, or even use galactic movement as a form of interstellar travel. If astronomers detect high-speed galaxies exhibiting controlled acceleration rather than purely natural motion, it could be a sign of large-scale engineering at work. Future observations will be crucial in determining whether these galaxies fit within known physical models or require new physics to explain their behavior. By analyzing their motion, astronomers may identify patterns revealing whether they travel randomly or as part of a larger cosmic structure. If they follow dark matter filaments, this could confirm the existence of gravitational highways shaping the universe. If they are concentrated near cosmic voids, this might indicate a previously unknown interaction between galaxies and dark energy. One of the most important breakthroughs could come from tracking the long-term trajectories of these cosmic speedsters. If their motion changes unexpectedly, defying known gravitational dynamics, it could suggest the presence of undiscovered forces. Additionally, if some of these galaxies appear to accelerate rather than simply maintaining constant speeds, this might indicate an unknown influence on their movement. Another groundbreaking discovery would be finding galaxies that appear to vanish. If a stellar system moves at extreme velocities and later disappears from observations, it might have crossed a cosmic boundary, such as the event horizon created by space expansion. This could provide direct evidence of galaxies escaping the observable universe, an idea long theorized but never confirmed. As observational technology advances, allowing astronomers to detect fainter and more distant objects, the study of ultra-fast galaxies will enter a new era. Next-generation observatories, including the Square-Kilometre Array and upgraded gravitational wave detectors, may uncover unknown aspects of galactic motion and interactions. If these high-velocity objects turn out to be more common than expected, it would suggest that the universe is far more dynamic than current models predict. Ultimately, these extreme galaxies could hold the key to solving some of cosmology's deepest mysteries. Whether they result from dark matter interactions, repulsion from voids, remnants of an ancient event, or even artificial constructs, their existence challenges fundamental astrophysical assumptions. Their study could not only redefine our understanding of galaxy evolution but also reshape our view of the universe itself. If these galaxies are more than just isolated anomalies, their movement could indicate that the universe's large-scale structure is far more active than previously thought. Their acceleration might be governed by unknown interactions between dark matter, dark energy, and intergalactic gravitational fields. If their motion cannot be fully explained by known mechanisms such as gravitational slingshots or black hole interactions, it could suggest that vast regions of space experience forces yet to be discovered. One of the most compelling possibilities is that these objects are responding to unknown gravitational waves or distortions in spacetime. If large-scale ripples in spacetime exist, perhaps caused by ancient cosmic events like the collision of supermassive black holes or remnants of a previous universe, they might subtly influence galaxy trajectories across billions of light-years. Future gravitational wave detectors could determine whether these galaxies are reacting to spacetime distortions beyond our current detection capabilities. Another intriguing question is whether these galaxies are linked to variations in dark energy. While dark energy is generally considered uniform, if high-speed galaxies tend to move toward or away from specific regions, it could mean that this force is unevenly distributed. Some parts of space might exert stronger repulsive forces, pushing entire galaxies to extreme velocities. If true, this would require a major revision of cosmological models, suggesting a far more complex expansion of the universe. It is also possible that these stellar formations reveal a new type of matter or interaction. If some galaxies accelerate in ways inconsistent with standard gravitational models, they might be affected by unknown particles or forces. For instance, if dark matter is not entirely passive but exhibits certain repulsive or dynamic properties under specific conditions, it might explain the unusual acceleration patterns observed. Alternatively, an undiscovered force acting at cosmic scales could first reveal its effects through these galaxies. A more radical idea is that these high-speed objects interact with hidden dimensions. Some string theory models propose that gravity may leak into additional spatial dimensions, causing unexpected deviations in galactic motion. If such galaxies are disproportionately found in certain regions of space, they might be interacting with higher dimensional structures, providing the first observational hint of extra dimensions. Another fascinating concept is whether ultra-fast galaxies function as natural time machines. Due to relativistic effects, objects moving at extreme velocities experience significant time dilation, where time slows relative to the rest of the universe. If a galaxy were moving near the speed of light, an external observer might witness it aging much more slowly than surrounding cosmic structures. If civilizations exist within such galaxies, they could experience time on a vastly different scale, effectively becoming time travelers relative to the broader universe. The detection of these galaxies also raises fundamental questions about their long-term fate. If they continue accelerating, do they reach a threshold beyond which they can no longer interact with the rest of the universe? If so, does this imply the existence of cosmic escape routes, where matter can permanently exit the observable cosmos? If one of these stellar systems were to cross such a boundary, it might appear to slow and fade from view, eventually becoming undetectable. Observing such a disappearance would be among the most extraordinary discoveries in modern cosmology. Another consideration is whether ultra-fast galaxies are indicators of an impending phase transition in the universe. If more of these stellar systems are found accelerating to extreme velocities over time, it could suggest a fundamental cosmic shift, possibly signaling a transition into a new state of physics. Some theoretical models propose that dark energy may eventually increase in strength, leading to the so-called Big Rip scenario, where galaxies, stars, and even atoms are torn apart as space expands at an accelerating rate. If these fast-moving galaxies are early signs of this process, they may be the first objects to reveal that the nature of the cosmos is evolving in ways we do not yet fully understand. As more advanced telescopes and computational models emerge, astronomers will be able to analyze high-velocity galaxies with unprecedented precision. If patterns emerge in their motion, they could reveal an underlying structure governing their trajectories. Some of these objects might also display unexpected compositions or energy signatures, suggesting interactions with forces beyond current understanding. Whether propelled by dark matter streams, gravitational distortions, or something even more exotic, these galaxies remain among the most enigmatic mysteries of the cosmos. The study of such extreme celestial objects has the potential to reshape our understanding of fundamental cosmic forces. Whether they are remnants of a previous cosmic cycle, indicators of hidden physics, or evidence of an undiscovered aspect of dark energy, their presence challenges the assumption that the universe is predictable and stable. Instead, they suggest a far more dynamic cosmos, where extreme motion and unknown interactions may one day redefine everything we know about space, time, and reality itself. If increasing numbers of fast-moving galaxies continue to be discovered, it could indicate that our understanding of the universe remains fundamentally incomplete. Their existence challenges traditional models of galaxy motion, hinting at unexpected forces at play or unknown interactions with cosmic structures. Future studies could determine whether these galaxies are simply anomalies or part of a larger, hidden pattern in cosmic evolution. One of the most crucial areas of research will be the long-term tracking of these cosmic travelers. If they exhibit variations in velocity or unexpected trajectory shifts, it could imply interactions with variable gravitational forces or invisible structures. Such deviations from expected motion would provide direct evidence of uncharted cosmic phenomena, potentially revealing undiscovered cosmic forces or gravitational anomalies. Advanced simulations and AI-driven analysis will be essential in mapping their paths and predicting their future movements. Another question is whether these galaxies interact differently with cosmic expansion. The accelerated expansion of the universe is attributed to dark energy, but hyperfast galaxies could provide new insights into how high-velocity objects behave within an expanding spacetime. If their movement deviates from standard cosmological expectations, it might suggest that space itself has hidden dynamics influencing their trajectories. Observing them over long time frames may offer clues as to whether space contains unknown factors that affect galaxies at extreme speeds. The role of dark matter in the motion of these high-speed stellar systems is another key question. If they exhibit velocities inconsistent with visible gravitational sources, it could suggest that dark matter plays a more active role in shaping their movement. Some theories propose that dark matter might not be entirely passive but could instead interact dynamically under specific conditions, forming invisible gravitational currents that direct galaxies along particular paths. If ultrafast galaxies are following these hidden flows, it would provide compelling evidence for the structure and behavior of dark matter on cosmic scales. There is also the possibility that these galaxies are linked to exotic astrophysical processes. Some hypotheses suggest the existence of previously unknown gravitational slingshot mechanisms capable of imparting immense velocity to entire stellar systems. If new classes of astrophysical events, such as interactions with rogue supermassive black holes or large-scale gravitational waves, are discovered, they could help explain why some galaxies achieve such extreme speeds. Investigating the environments around these objects could reveal whether they originate from regions of high gravitational instability. Another avenue of research is whether high-velocity galaxies represent a previously unknown evolutionary pathway for galactic systems. If some galaxies are ejected from dense clusters or experience prolonged high-speed motion through intergalactic space, they may undergo unique evolutionary processes. A galaxy moving at extreme velocity might lose its gas more rapidly, reducing its ability to form new stars. Over time, it could evolve into a dark, inactive system, devoid of significant star formation. If astronomers identify quiescent galaxies that appear to have once been high-speed objects, it could indicate that these stellar systems aged differently due to their extreme motion. Another intriguing possibility is that rapidly moving galaxies could serve as natural laboratories for testing relativistic physics on a galactic scale. Since objects moving at near-light speeds experience time dilation and other relativistic effects, their internal physics may subtly differ from stationary galaxies. If ultrafast galaxies exhibit unusual energy distributions or unexpected cosmic ray activity, they could provide an unprecedented real-world test of Einstein's theories at galactic scales. The potential for these galaxies to reveal hidden cosmic structures is another key area of study. If they consistently move toward or away from specific regions of space, it could suggest the presence of unseen mass concentrations, variations in dark energy, or even exotic gravitational anomalies. Some researchers speculate that hyperfast galaxies may act as natural probes of the universe's invisible framework, uncovering structures that otherwise remain undetectable. Large-scale surveys mapping their trajectories could provide new insights into the hidden architecture of spacetime. The ultimate fate of these galaxies is uncertain. If one is moving at its, does it eventually slow down interactions, or does it continue indefinitely? If some appear to gain velocity over, it might indicate with large-scale cosmic flows or even hidden dimensions. Conversely, if they eventually decelerate, it could suggest that intergalactic drag, dark matter interactions, or unknown gravitational effects gradually reduce their energy over billions of years. If any of these galaxies were observed to vanish from astronomical surveys, the implications would be profound. Such a discovery might suggest that certain galaxies are crossing into regions of space fundamentally different from our own, potentially supporting theories of cosmic gateways, wormholes, or even the multiverse. If a fast-traveling galaxy were to disappear without a trace, it would be among the most extraordinary astronomical findings in history, requiring a radical reconsideration of cosmic boundaries. As technology advances, the study of ultra-fast galaxies is likely to become one of the most significant fields in astrophysics. The ability to track them over millions or even billions of years could help resolve some of the biggest questions about the structure and evolution of the cosmos. Whether they reveal new forces, uncover exotic physics, or simply challenge our understanding of gravity on the largest scales, these extreme galaxies could hold the key to the next great discoveries in astrophysics. If these high-speed objects are part of a larger, hidden structure within the universe, their continued study may unveil aspects of the cosmos that remain undetected. They could be following unseen gravitational currents, responding to forces beyond our current understanding, or even moving toward a final destination beyond the limits of observable space. Their behavior might be signaling the presence of undiscovered cosmic phenomena, making them one of the most promising astrophysical mysteries of our time. One of the biggest questions surrounding ultra-fast galaxies is whether their trajectories are entirely random or if they exhibit patterns that suggest an underlying order. If their motion aligns with large-scale structures, such as cosmic filaments or dark matter streams, it would provide strong evidence that these stellar systems interact with an invisible framework shaping the movement of matter across billions of light-years. Future deep space surveys will be crucial in determining whether these galaxies follow specific paths or are simply the result of chaotic gravitational interactions. The possibility that hypervelocity galaxies are connected to large-scale cosmic expansion raises additional questions. If they are accelerating beyond expected limits, it could indicate that space itself does not expand uniformly. Some cosmologists propose that different regions of the universe may expand at varying rates due to fluctuations in dark energy density. If these high-speed galaxies are concentrated in areas of anomalous expansion, it might suggest that the acceleration of the universe is more complex than previously thought. Another potential factor influencing these fast-moving stellar systems could be unknown astrophysical events. While many are believed to have been ejected due to interactions with supermassive black holes or gravitational slingshots within dense clusters, there may be other unidentified mechanisms at play. If some galaxies reach extreme speeds without any apparent interactions, it could indicate the existence of new cosmic forces, undiscovered astrophysical explosions, or interactions with exotic forms of matter. A more radical hypothesis suggests that these galaxies might be revealing new physical laws that only become apparent on extremely large scales. In standard physics, galaxies should not be able to exceed certain velocity limits without external forces acting upon them. If some ultrafast galaxies are moving beyond these expected thresholds, it could suggest the presence of an unknown force or even a modification of general relativity that applies on the scale of galaxy clusters and beyond. If confirmed, this could revolutionize our understanding of gravity and possibly lead to a new theory that unifies relativity with quantum mechanics. Some physicists even speculate that hypervelocity galaxies might be linked to